Okay, this is going to be the video for differential equations section 7.5, the delta Dirac function or Dirac Delta Function. This is the last topic we're going to cover in the Laplace transforms chapter, and this is a short one, just to introduce one more function and its Laplace transform that's useful in modeling certain unusual circumstances. So what would the simplest Laplace transform that we've seen so far that's in the regular table is the Laplace transform of 1, which is 1 over s. Could there be any simpler Laplace transform than just 1 over s? Like, could we have a Laplace transform of a function where the Laplace transform is simply the constant 1? The answer is yes, but the function is not a normal function. So that's what we're going to talk about here. We're going to talk about something called the idea of a unit impulse. So far, we've been able to model things like driving functions for systems using the unit step function, which would allow us to, for example, turn on a driving function at a time t equals 2, for example. But once the function is on, it exerts its force for some definite period of time, right? But instead, what if we wanted to model something like what happens with the vibrations of an object if it's struck by another object? So there's a driving function, but it only applies its force for an infinitesimally small period of time, right? How would we deal with that? Okay, so, well, first we can define such a function, piecewise defined, and this is actually called the unit impulse function. It's given the lowercase delta a. This a indicates this is the base function, t minus t0, where the time where we apply this impulse of energy is at t0, so that's a constant. Okay, and then the function is defined to be 0 up until we get near that time, and then we take the time of application and we surround it with a little tiny, very small distance here. We go t0 minus a and then t0 plus a, where a is understood to be a small amount of time. So we say, okay, so the force has an application that begins at some level, starting at a minus the time t0, and then it continues until the time t0 plus a. And then we adjust this height such that the area under this curve is equal to 1. So if this would be a here, half of a, we would have to have a half of, this has to be a half of an a height here, so that this length times this width ends up being a 1. So we define it to have that 1 over 2a height here, and then 0 elsewhere, such that this area is 1. So we could say the integral from 0 to infinity of this delta a function dt is always defined to be equal to 1. Okay, now it's difficult to work with this improper integral. So instead, what we do is we in practice work with another type of function, an impulse function. It's not really a function, we'll say function in quotes, that approximates this function with a limit. So if we remove the little a from this delta and just call it delta t minus t0, and we just say, okay, take that piecewise defined function and take the limit as a approaches 0 of that, okay? Then we allow this width to be smaller and smaller. So effectively what's happening is this. We're saying, okay, now what would happen if I were to allow this function to be smaller? So I reduced a. Well, then this height would have to be larger to compensate, right? Or if I made it really, really small, right, then there would be really tiny little width with an almost infinite height, right? But the area under that curve would still be 1, right? So as you bring the width in, the height has to grow to compensate to make the area under the curve 1. So this function, this delta function here, is essentially, it's a spike that is almost infinitely tall, but it's only applied for a negligibly almost 0 period of time, such that the area is understood to be 1. Okay, so you could say that this function is basically infinity at t is 0 and it's 0 elsewhere, but it has this property that we've arranged things so that the area stays 1. So it's not really a normal function, but this special impulse, special unit impulse, it has a name. It's called the Dirac Delta Function, named after Dirac, who was a mathematician, physicist, who first described this. And we can use this function as a driving function whenever we want to model something called an impulse, something where like an object is applying its force over a negligible period of time. So for example, if you wanted to model an airplane wing as like a spring mass system to see how it vibrates, and then imagine what happens if a bird impacts, like flies into the plane's wing, right? So it's hitting the wing and it imparts a force, but that force only acts over an infinitesimal amount of time. That is modeled with a Dirac Delta function. All right, so it can be shown, and I've got a separate PDF if you're interested in the derivation of this, that the Laplace transform of the Dirac Delta function at time t is 0, or t0, a constant, is e to the minus st0. It's like the Laplace transform of the unit step function, but without the dividing by s. And then if time t0 is 0, it turns out that it's e to the 0 and therefore 1. So in fact, we do have a function whose Laplace transform would be 1, and that would be a Dirac delta function if the time of application was 0. All right, so I'm just going to show you one example of how this would be used. Let's say that you have a second order differential equation. Maybe it represents an undamped mass spring system. Maybe we have the mass is initially displaced and released, so we displace it 1 downward and we release it with initial velocity of 0, so it's oscillating on its own. And then at some later time, 2 pi, 6.28 seconds later or something, we hit this mass with a hammer. With an amplitude of 4, but it only applies over this tiny amount of period of time, an infinitesimal amount of time. What would happen to the solution curve for the displacement of the mass? So we could take the derivative of this whole expression, right? The derivative of y double prime would be s squared ys minus sy0 minus y prime 0. And the derivative of the y is this. And the derivative here is 4 times the Laplace transform. I shouldn't say the derivative, the Laplace transform. The Laplace transform of this delta is 4 e to the minus 2 pi s. Okay, you could apply these initial conditions. Y0 is 1, y prime of 0 is 0. Gather all the terms over here and divide through by the leading coefficient to solve for capital Y of s. You'd get s over s squared plus 1 plus 4 times 1 over s squared plus 1 e to the minus 2 pi s. And then when we take the inverse Laplace to go back to the time domain, we have yt. The inverse Laplace of s over s squared plus 1 would be cosine of t. This would be 4. And then this is a time-shifted version of the sine wave. 1 over s squared plus 1 would be sine, but shifted in time to 2 pi. So sine of t minus 2 pi, also unit step function t minus 2 pi. And then we know that if we are on a unit circle and we subtract 2 pi, we get to the same place. So sine of t minus 2 pi is just the same as sine of t. So that means we would have y of t as cosine of t, that's from this term, plus 4 sine of t unit step function t minus 2 pi. And if you were to graph that function, it would look like this. So what happens is, from displacing the mass initially and releasing it, it starts oscillating at its own natural frequency set by the spring constant in gravity. And then when you strike it with a hammer at 2 pi seconds, then there's more energy in the system, so it keeps oscillating at the natural frequency, but now with a higher amplitude, starting at the location where it was there. All right, so that's how we would use the Dirac delta function. We're not going to use it much on the test or anything. I'm not even sure if we put it on the test, but because we want to be complete and show how to model something that is a driving function that applies over an infinitesimally small amount of time, we have this function called the Dirac delta function. And that should be enough to do the short homework assignment on it for tonight on 7.5.